Okay, so our next speaker is CM Chandrashekar from the Institute for Mathematical Science in Chennai, and he's going to talk about simulating quantum systems and quantum computation using quantum works. Please, stage is yours.
Thank you very much. It's working. So, simulating quantum systems is one of the main research topic we are working on in our group. And the tool for us to simulate has been quantum walks. Quantum walk is one of the most simplest way of describing the dynamics of a single particle, exploiting the superposition, interference. And it's also a very rich resource for generating entanglement between spin degree of freedom and part degree of freedom. If you're talking in photonics language, it can be polarization and part degree. If you're talking about some other system, it can be like electrons, or it can be even superconducting qubits. So there are always different degrees of freedom. So it gives a rich resource to control entangle between two Hilbert spaces. So using that as a tool, we are developing some algorithms. I mean, like modified versions of quantum walks to simulate few physical systems. And I'll try to give some examples of the physical systems which we have been simulating, and also how we can do quantum computation using quantum walk. As I said, it's a rich resource to control entangle between two Hilbert spaces. You can also do quantum operations and can serve as a foundational block for quantum computing. So when we talk about simulations, the simple idea has been there. It's something which Feynman also started in his talk, where why quantum computing is important, because we had to simulate physical systems in real. It's not about advantages which we are talking about right now, or it's not about the speed up we are talking about, but just trying to mimic the nature exactly the way they do using some other systems. So you can have some systems. We have to come up with some approximations of their initial state. We have to come up with some unitary operators or roughly unitary operators, so that we end up having some output which mimics what the nature does. So the main objective of any simulator which we are thinking of to build is to harness the controllable quantum evolution of one system using using another accessible complex system. And the other one would be to look at the resources needed. So you need to have some resources which is which is accessible. It should not be an exponentially required one. And so these are the two main objectives for us to look at quantum simulation. In that, there's been two wide topics, in the sense it has been divided into two prominent subfields. One is the digital quantum simulations. So the most standard way has been you have some Hamiltonian. It can be a complex Hamiltonian of any complex quantum system. So you have to come up with some approximations of them. It can discretizing them, breaking them up into subsets, so that you can eventually boil them or bring them down to some gate operations, so that you can do some sequences of it. So there are various methods already available. People have been working on it for many decades now. And the other one is an analog simulator. In an analog simulator, sometimes you will not be able to simulate anything and everything you want. You will have some system which is closely mimicking the Hamiltonian of the system which you want to simulate, but some parameters can be controlled in that. So that will help you to tune and then simulate the other system which is not accessible. So these are the two broad topic of to way to approach quantum simulations. So for us, digital simulations, the way we try to follow is something like this. We have a complex quantum system. It can be anything, where it can be treated as an open system, or it can be a clean quantum mechanical system with few qubits, or it can be few molecules interacting. And then you have to come up with an algorithm, so that you have to try to see what is the possible model to describe the dynamics in that system. And once you have an operational form for that, you need to build a quantum circuits, so that you can actually go to a quantum simulator, which is a digital simulator, and then implement them. So which means that it has to be implemented on a quantum hardware. So this just depicts that you have some qubit system. I mean, you have some physical system. You come up with an algorithm, build them up as some so many number of qubits, like it can be 3, 4, 5, and then implement it on a physical system. So why we think quantum walk is a very rich resource. I'll try to come to that. So it's not something very new. For centuries, classical random walk has helped us to model various things in nature. The idea has simply been you toss a coin, you move to the left or right, and then you end up having some output, like after some time evolution, you'll find the particle somewhere. But that might not be a right answer. You try to repeat them, and that's been. And now this is just a one-dimensional one. If you want to take a complex system, it can be some polymer dynamics or some other dynamics, where you make these dynamics very complicated. You can call it a self-avoiding walk or various other complex and two-dimensional with certain restrictions. Then you start modeling those systems as accurately as possible. And the quantum version of this has been like you replace the walker with a quantum particle. So what is the degree of freedom which we get from quantum particle? It's a superposition. It means that you toss a coin, but instead of just going to head or tail, you can be in superposition. So it means that it allows you to take the path both left and right simultaneously until you make a measurement and collapse the wave packet. If you're not making a measurement, it evolves in superposition of position space. Now that's exactly is what is happening here. Like there is a superposition of evolution, and there's always a finite probability of finding a particle at every position space. So you collapse and then you get it. Now this was not something which physicists picked up in the early time. It was more of computer scientists found a very interesting feature here. The quadratic faster spreading of particle in position space, which is quadratic in time, was a resource for algorithms. Various quantum algorithms, such algorithms were developed based on it. So now this, if you are looking at it, I can take two positions, and they also would have some kind of entanglement between them. I mean, there is an entanglement between the walker and the position space, because there is always some information of position space which I will get if I am collapsing and looking at the particle. It can be maximally or weakly, or there is always some entanglement between them. So I can control the dynamics. So mathematical construct for this has been, you have a Hilbert space, which is a coin in the position space. It can be a spin up and spin down, which is head and tail, and the position space. So it's a standard superposition. For in one-dimensional walk, I just had to bring it into a superposition. And evolution is a coin operator. I mean, you say you toss a coin, instead of head and tail, you have a unitary operator, which brings it in the superpositions. Like as I said, it's a spin up will move to left, spin down will move to right. So which means that you are continuously evolving. So now this is what the probability distribution looks like. You can have you will have what you call close to ballistic, the widespread in position space. The classical random walk would have a Gaussian distribution. Now this has some, it can simulate various things. It can simulate dynamics of Dirac equation, directed transport, topological insulators, and people have shown that it can simulate more than that. Many of them. So now these are not random evolutions. These are pure unitary evolutions. Though I said there's a classical random walk and this is quantum walk, these are not random. The evolutions are unitary, reversible. And one can control the dynamics the way we want. If I'm just beginning my walker itself with some spin-up state, then I would have an asymmetric distribution to the left, or if it's spin down, it's to the right. And if I bring in with this I phase, like initial state in superposition of I, it means that where I begin in the block sphere defines the way I get my probability distribution. If I have this, then I would have asymmetric distributions. Now, the coin parameter, or it's said the way you have superposition of 0 and or like spin up and spin down, the theta one which defines what is spread. So this should have been 75. So it can spread to wide. It can be ballistic, like 2 peaks, or it can give you some interference pattern, or it can also be narrowed down. So now one can have a control on the spreading in a given position space, and also have a control on the way to the left and right asymmetry by oops. Okay. So the left and right asymmetry also in it. So the coin and the initial state will help us to have a distribution the way we want in one dimension. Now this is not true just for one dimensional. So there's a lot of work which people have done to look at two-dimensional spaces and higher dimensional coin operation, and you can have a control. Like if I am given a position space, either it's 1 or 2 dimension, I can define the initial state and the evolution operators and have the desired probability distribution output on the position space. So that is a very rich resource. So now one of the simple examples we try to look at simulating a simple system is like disorder, right? So disorder is not noise here. It's like, you have a coin operator. Each time you have a random coin operator with different values. So you can think of multiple kind of, like each time I'm operating a different coin operator, then it call it as temporal disorder. Or I can take a position space. At each position space, I define different probability of going to the left and right. It's a predetermined. That can also be considered a spatial disorder. and also be a fluctuating, both spatial and temporal disorder. These are like in standard ways of understanding or studying disordered systems. Now, what is very interesting here is that if I start looking at the spatial disorder, 100% disorder, I would end up having a strong localization, something, the quantum wave packet, which was spreading quadratically faster in position space. The moment you are introducing a spatial disorder, you would end up having a localization, which is actually, if you are looking at it and going back to a condensed matter literature and then see, this is Anderson localization effect. Like, you have a lattice and then you introduce some disorder in it, the electron localizes at a strongly localized at a given positions. Now, this is not a physical system which we considered to have an electron or how the disorder is, but this is an algorithm which is simulating an Anderson localization effect. Now, the temporal disorder is something which we call as close to a weak localization effect, which is again, people study this dynamics in condensed matter systems. So you can have a controlled coin operations and simulate this strong localization, weak localization, those effects. Now, with disorder, we can see how the route towards, we can calculate localization length and route towards localization. One of the important, interesting thing which has come out of quantum information theory approach to such kind of dynamics is also to understand entanglement between them. Like what has been shown is that the Anderson localization, which you see, that electron or something which is very strongly localized position space, is also strongly entangled between the particle position space and the particle are very strongly entangled compared to the standard quantum walk or any other dynamics. So, which means that one can study entanglement behavior in such kind of systems, and one can also scale it up into. So now, if you are looking at the way it evolves in time, so there's just a picture, and one can calculate analytically because we have coin operator, we have wave function. We can write down calculate the group velocity and show that with long time you end up having a localization effect in the. So now one of the interesting thing which came up as a problem under quantum walk, it was there for many years, is like coming up with an exact algorithm to simulate Dirac equation. So Dirac equation mainly is because quantum walk also has spins, and Dirac equation deals with spin degree of freedom. So the standard textbook expression form is this. So Dirac equation has a time derivative term, Hamiltonian, mass, everything. So if you can have an algorithm to simulate Dirac equation, which means that you can simulate most of the dynamics in nature which are following Dirac equation. It can be a condensed matter system, or it can also be an high energy system. So even before quantum information era, so there has been an approach like, you have most of the time when we go to computers, we discretize it and then write an algorithm and implement it in classical computers. So what was done by field theory researchers is like come up with a cellular automata model where you have a unitary operator of this form, which kind of mimics the Dirac equation. Now, if you look at it, you have again it, t are the translation term, which goes from x to x minus 1, x to x plus 1. So these are the translation terms, and these are also the off-diagonal elements have no translational component, but the cellular automata model mimics Dirac equation, and that's something which people have taken. Now, but if I go back to quantum walk, which I described, like you move to the left and you move to the right simultaneously and look at it, the unitary operator form for that, coin and shift, if I'm writing it together, it takes this form. Now, if I'm looking at these two, there is some similarity, but there is also something which are not matching, which is the off-diagonal element. Off-diagonal terms as translation in quantum walk, but in the cellular automata model, it doesn't have. So there were quite a bit of literature which people tried to see that, how do we tweak around the quantum walk so that it exactly mimic Dirac equation. Now, if you try to understand them pictorially and see how the quantum walk evolves, this is what I described. You toss a coin, but if I'm breaking down the lattice, there you'll find a lot of position space, alternate position space unoccupied at each time of step. But this is what the probability distribution we are going to get. But what the simulation of this expression, this cellular automata model looks like, is something like this. You are not just going to the left and right. There is also some component which is falling down without evolving. And this is an effect of mass term there. The Dirac equation has a mass component, and it's an effect of mass term. And now that mass term allows you some oscillations between the parities of the Walker, which means that you get something called a Zitterbong oscillation, which is also studied in high energy physics. Like So now these oscillations correspond to Jitterbug oscillations, which are not seen in quantum walk, but cellular automata model gives this. So this was addressed long back. When people had tried to see, okay, if I have a quantum walk, a massless Dirac equation, if I'm making it massless, then there is no red line here, then the quantum walk can simulate a massless Dirac equation. But how do we simulate massive Dirac equation was an open problem for quite some years in the quantum walk field. Now what one has to do is that tweak the quantum walk such that you end up having the off diagonal element and not having a translation component. So the simple solution was to see, I have to make a walker retain or be in the same position along with moving to the left and right, and it has to satisfy unitary condition. I can't just have a single evolution which does that. It won't fit the unitary bill. So what one came up with a split step model, which means that at any given time, I toss a coin, there's a probability of an amplitude which says remain at the same position, move to the left, and the next one would be toss a coin, same position, move to the left, right. So which means that you would end up split each step into two steps, which is just moves to the left and moves to the right with different parameter. And that exactly, if I'm writing down into a unitary operator form, takes the form as your Dirac cellular automata model. So which means that one of the theta will exactly mimic the mass value. So which means that I can have a mass term, and if mass is higher or mass is lower, I can fix the theta accordingly. So which means that the mass variation can be captured with this theta. So mass, which means that mass and the velocity term would be a sine theta term. So which means the theta will mimic the mass. So now this kind of helps ones to simulate, and now it also gives us a rich dynamics here to that I can now start calculating the entanglement between the spin degrees of freedom and the spin and the spatial degree of freedom of any Dirac particle, and also generate gapped and gapless Dirac equations, which people are studying in condensed matter system. And this leads to simulating topological insulators also, which follow Dirac equation. There's been quite a few literature in this direction. So there has been quite a few literature. We try to fix the mass term and come to an exact simulation model. So what would be interesting now is to go from a single particle and see how I can get into a many particle dynamics, right? Because I can have 3 Dirac equations. One of the problems which we picked up was to see the Newton oscillation, which is one of the well-studied phenomena or well-understood phenomena. There are 3 flavors in neutrinos, which is E, mu, and tau. There is a flavor change which happens. And during the propagation in position space, the flavors change from one to the other. And the standard model, which tries to describe, considered the neutrinos are massless, and they are very weakly interacting particles. But the experimental observations disagreed with it completely, and they came up with some correct interpretations, that is neutrinos are massive and leptons mix, which means that there is a mixing of flavors between these 3. And this is just what is there in the standard Newton oscillations. It's a precursor to see how I can map this into a quantum walk and simulate the dynamics in it, right? So now Newton oscillations indicates incompleteness of standard model, which means that one still has to come up with some understanding of the whole dynamics there, so that you can fix some open problems in understanding Newton oscillations. Of course, that's not our intention. Our intention is only try to see how I can mimic them. So again, the mathematical construct for Newton oscillation is that it's a superposition of mass eigenstate. So I have 3 flavors, but I can write them as a superposition of mass eigenstate. There will be a unitary transformation on the quantum basis. I can write them all, the mixing matrix. This unitary operation, which is the one which transfers flavor one to the other, can be broken down into a simple mixing matrices. And this is just a free Dirac Hamiltonian. We don't have to worry too much about all the details here. All that it would be require is a propagation wave solution, and then transition probability, because our interest is try to focus on transition probability, like one flavor to another flavor, how it happens. So you have an unitary operator, and the states evolves, and from that you can calculate a translation probability. Like now, how do we go about with quantum walk? It's instead of taking a single particle walker, I can take 3 particle walker, which means that I will end up having, if I'm having a 3 particle, I would have 8 basis states, because if I'm taking a 3 qubit system or a 3 walker, but I can just choose 6 of them and ignore 2 of them and write down the basis states of them, which means that I have 3 pairs of Newtonov flavors, which is 1 and 2, 3 and 4, 5 and 6. This flavors oscillations between them, and the Hilbert space of them would be just the sum of them. So now the evolution would be the coin and shift operator on each one of those three flavors with the mixing. You begin with an initial state. So we can come up with a 3-qubit vector space represented by the same span by this grid, which means that 0, 0, 0 represents state 1, 2, 3, 5, 6. So now I can have if I'm writing down the coin operation, which I wrote in the previous expression, it takes the form like this. Shift operator would be simplified to have something which moves to the left and right, same model. As I said, because of the requirement of only 6 basis state, the 2 are considered 0 and we are not going to use them. And I can write down the mass eigenstates for the neutrino flavors. At 3 mass eigenstate, I can write down. So this is just like preparing I'm defining a coin operator, I'm defining a shift operator, and I'm defining the mass eigenstate for the flavor option, so that I can apply these operators on them and then get an output. So what interestingly we observe is that if I can, this is what experimentalists have, and this is what the neutrino oscillations from one flavor to the other shows with some high energy and long distance when they measure. But if you implement few thousands of, few hundreds and thousands of steps of quantum walk, I can reproduce them exactly the way we see in the real experimental one. So which means that one can simulate a neutrino flavor oscillation using a 3-qubit system if I'm implementing a quantum walk there. So there's a rich use of polarization and part degrees of freedom, or spin and part degrees of freedom in such kind of system. And what interestingly it allows us also to see the correlations between the flavors when their dynamics is happening, and the correlation in spatial degrees of freedom also. So the details we have reported in the paper, I'm not touching this part, because my interest is to see how you can actually build up an algorithm to simulate some of the physical systems. Now, these are all simulated in the classical computers. One can say that you are implementing those algorithms in classical computers, and why do we need quantum bits or computers? But this is helping us to model them such that you can address much more higher complex problems with quantum computers and later on. Now, this is again, on the numerical simulations and the mathematical framework on which we have developed it. If I had to go and simulate them on a real quantum computers, I need to convert. Like in the initial slide, I mentioned that you need to have a physical system. You have to come up with a unitary evolution such that you have those two parts I explained. Now I have to come up with the quantum circuits, which I can take it to a quantum computers and then implement. Now these are not quite trivial, because if I go to a literature, or like if I just straight away see the unitary operators I wrote and write quantum gates for them, it somehow becomes like this, which is a highly complicated controlled NOT gates. If I go to any quantum processors and then say I want to implement this, they say the systems are not ready for it. So one has to come up with an optimization of circuits. So I'm not going to the details of methods we try to follow, but we try to map. For example, I have to implement, I have an access to 5-qubit system, right? So now if I have an access to 5-qubit system, there's a position space and spin degree of freedom for the walker. I can map the position space with the given 4-qubit, because 1 qubit will be used for a spin degree of freedom, position space is mapped. And this is an optimal mapping which we have done, but how we got it, it's probably a simple redundancy experiment, calculations one has to do. But this is a mapping we tried to do, so that given an initial state, what is the minimum circuit depth I would have, so that I can go and implement it on a, right? So these are the standard setup which I had. Like for example, I can choose different mapping, and I can just have a control NOT gate and the poly operators. The coin is a simple, any rotation on the qubit system. So if I have to implement 5 steps here, now in a standard quantum walk model, I described it's a coin and shift operator every time. But if I'm breaking down into quantum circuit, you'd see here for a first step, second step, third step, the circuits are not the same. I'm not just repeating the same circuit, because if I had to implement it on as an universal operation, it becomes very, very complicated. So we get into system specific, initial state specific, then you can reduce the complexity of quantum circuit. And we come up with a few optimal configurations of quantum circuits. These are just 2 simple forms. But the simplest form was implemented on an ion trap system in collaboration with Maryland, where to implement even 5 steps of this oscillation, we needed about 78 and 32 single and 2 qubit gate operations. But one could show that you can simulate Dirac equations, control the mimic the mass parameter and look at it. Though it's a small number of steps, but gives some idea that you can, now you can play around with coin operators and try to simulate even curvature and various other things just been shown in the literature. So now the other problem which we, after looking at it, I mean, said the other problem would be to even see how one can mimic an open quantum system, because you have a lot of systems in nature where you have some energy falling in, it takes various particular path, and there can be noise effect and the superposition of multiple paths which takes. And this is one of the standard models which people are like, protein complexes which people have studied, where quantum effect has been observed in a transport models. And again, this is not settled yet because there are various models on how to simulate or like to mimic FMO. And there has always been a disagreement with, even last year, there's been a disagreement with all the existing model, and people have come up with different model. It's mainly because you are not been able to explicitly map the experimental observations to a theoretical model in all aspects, right? There is one in packets we have been able to address them. And this also tries to address. So you are trying to, again, use a quantum walk model here. You have toss a coin, you have an hopping component, you also have a self-looping component, and there's also a noise component you add into that. And you come up with, so it means that you have, this is what one, if I'm just taking a two-side, I can think of a quantum jump and unitary evolution is a quantum walk and a self-looping effect. I can break them up into something which is a unitary and a quantum jump. So if I try to do that just for like, now this is only for a two-side, right? If I have that, the FMO complex as 7-side, if I try to do that for a 7-side, the same model, I scale it up, then one can actually fix a parameter and try to see if the energy, if the photon is falling in 1 or 6, it has an high probability of reaching 4 or 5. If it's falling in any other, it may not reach, you will not reach the reaction center, right? So now that can be shown explicitly by a mathematical framework. We can write down the quantum walk with the environmental interactions and see if it's starting from 1, it reaches 4 or 5, it reaches 3 or 4, but or else it won't have a probability of reaching anywhere. And it also shows that if I don't have a noise, then it will only be an oscillation between where it starts and it goes back, it never reaches your reaction center. So it clearly gives, the framework gives an evidence that it is an environment which is helping a direct transport from point A to B. If there was no environment, it would not have reached B, it would have been oscillating. It's a purely quantum mechanical evolution. And this is what it is, oscillation, where you don't have any transport, confirmed transport like the way it is. So this is with noise, the top two and the bottom two are without noise. Now this is again a mathematical framework we do, and you can study the effect of temperature, all of those things, which say how the temperature will decrease the population of reaching, and one can say map like what is these algae which people have observed and have tried to study, and what is the experimental observations in given temperature, and how we can fix the parameters in the model. If I have to go to quantum computers and implement them, all that I would need is 3-qubit system, and I don't need more than that because there's only 7 sites there. So which means that, but I also had to mimic environment there. So I can consider 2 qubits, where the way we have, again, the details are not here. I mean, the cross operations or like how the mathematical framework is developed. But the simple idea would be like I have 3-qubit system, and there are 2 more qubits which act as path, and then you can mimic the whole effect. Like there's a quantum circuit one can break down. But now, if I had to give a count, this needs some hundreds of 1 and 2 qubit gates just to implement the whole dynamics on it in an existing system. But again, there are different models which people have come up with to try to get rid of or optimize the environmental effect and still go to IBM and implement this kind of models. Now, all the pictures of localization or a Dirac equation or this FMO complex are all based on, at least the way I'm trying to present is that it's in the quantum walk framework, right? You can get rid of it and also still present. But for me, it looks much more simpler to have a stool of coin and shift operator where you can just modify these 2 things and then say for which physical system I have to fit and then study them. And that's something which we try to look at it. Now, there's one thing which came as a hint. I try to quickly conclude with the last part of why we find it's very important to control this. The control of this dynamics is very important for quantum computation. Right? So there is when I said when we implemented quantum walk on ion trap system, one of the things which we did was you have a position space, and we map the position space into qubit system, right? Just like this. So quantum walk, quantum mechanics is a reversible process, so which means that if I have an access to position space, then I can also mimic qubits. Let's not talk about resource for the time being. It may need a lot of position space to mimic so many number of qubits, but in principle, if I even have an access to position space, I can mimic qubit. Now, using that as an idea, so we wanted to see how we can come up with. In fact, there are other earlier models where people have come up with a quantum walk as a primitive for quantum computation. If you have a complete controllable quantum walks, you can do quantum computation. There has been few models existing, but how do you break it down into a practical model was something which we carried forward, where you have a particle and then you have position space. Like if I have position space, I can label them 0 and 1, just like the way we did when we did an experimental implementation, right? So now this is 1 qubit, and now if I have this particle sitting on it, then I can create a 2 qubit system. If I have a lattice with the 4 position space, then I can bring in this particle here, and then I can create a 3 qubit system. Because 2 plus 2 and 2 into 2 is same for me, so I don't have any problem here with the scalability or what you call the resources needed in position space. At least for up to 3 qubit system, using a 1 particle, I can create. Right? So coin and shift operator, again, I can simply come up with a very generic coin operation and a modified version of shift operator. As I said, I have a square lattice at some probability or with some amplitude, it has to move to the left or it can remain same. I can write down a very generic operator of moving to the left and right and have a universal set of operation. A shift operator, coin and the identity operator should be able to do a complete quantum computation. And this has been, this is like Adamard on the coin operator would be on the first qubit. And if I have a 2 position space, I just have to have a coin and shift at both the point. And if I have to have an Adamard on the second, because these are 2 things now. One is a real qubit or real particle, and the other one is a position space. Now, because the second qubit is a position space, which means that action has to be identical on both of them for some operations, and it has to be done very uniformly. And this is the way we do all the standard like control not gate. Control not is a lot more easier in a 2 qubit operations. And even Toffoli gate, error corrections, everything could be worked out. And we have tried to come up with the scalability. But of course, it's not very trivial how I take this into physical system. We have some example. I can have a square lattices like this, which mimic 2 qubits at every time, and I have particle which can be in superposition this of them. So it means I can create a tensor product state to mimic a larger number of qubits. Of course, it looked like a very mathematical one. Like that was one of the criticism we had from referees, that mathematically everything sounds good. It doesn't look physical, like how do we take it physically? But of course, we tried and we have actually generated few qubits in our lab. I mean, we have theoreticians, but we also have a lab. We are doing both theory and experiments. So the simplest examples, like we have few qubits, like this is what I was telling, right? You have a quantum walker, it moves to the left and right. So if I'm having a 1-step and 2-step walk, this is what we have been discussing. This is what has been implemented in various other systems. So I have 4 paths. I mean, in fact, it is an interference here, but still there is one polarization and a different polarization coming here. So they won't interfere. They are different polarization. So I can have 4 detectors and I can label them H0, V0, H1, V1. So it is 0, 0, 0, 1, 1, 0, 1, 1. Now, by controlling the splitting of the polarization in multiple paths, I can have a control over the probabilities of all the 4 basis states. This is a simple 2 qubit system which one can generate. Now, how do I do gate operations between them? The schemes which I presented can be mapped down here. Like if I have to do a control gate operation, then I need to bring in interference between those paths. It means the single photon interference has to be created. That's the trickier part. Of course, we have done that to demonstrate a few things. So one can now show there's the correlation between polarization and path degree of freedom, which means that there's 2 Hilbert spaces. This is H and V. Because I can control the splitting between the paths, I can access all the basis states of the 2 qubit system which I have mapped here, which means that I can show violation of Bell's inequality between the 2 Hilbert spaces. Of course, not talking about non-locality or any of those things here, but we can still see the violation of Bell's inequality between these 2 qubit systems. So now doing gate operations, like I said, the moment I create a 2 qubit system, the paths has to be interfered. Now these has to be a proper single photon interference. Very precise interferometers are needed. So you can implement an Adamard operator, and you can also implement, so Yeah, I'm almost done. So this is actually a theoretical model which we have developed, and these are the experimental results where we have actually calculated the fidelities of the gate operations of all the 1 and 2 qubit gate operations. And of course, some of them, it's mainly because we are using bulk optics and the precision of the fidelities are slightly low, where the interference are involved, because even a small fluctuations in air, it deviates us and gets slightly lower fidelity, particularly in Adama 2. The second one is path degree of freedom, it's 92, but we are trying to improve them. So now using this, we can actually have a complete 3-qubit system where again path and the polarization degree of freedom, but it's a single photon, but still can do a 3-qubit operations. So we had demonstrated some examples of generating a 4-qubit system and then generate specific states, tunable specific states for us, which can be used for cryptographic applications. And a 6-qubit system, the way we did, what we have done is, instead of taking a single photon, we have taken entangled photons, and one of the photon is creating a 3-qubit, other photon is creating a 3-qubit. So now these two are entangled, so which means that I can generate a 6-qubit GZ state. The standard GZ state for 6-qubit would be of this form, but the way we do it for our scheme is these two are entangled first, which means that these two are entangled, and then you create control NOT gate between them and have a 6-qubit system. So yeah, one can verify them by looking at the occupancy at each point, which is almost doing an entanglement witness of them to show that they are clearly a clean GZ state. It's about 98% efficiency. Okay, so I to acknowledge a lot of them here because doing both theory and experiment support from colleagues from various places, the funding offices in the country or outside for very generous support for us. So thank you very much for your.
Yes. So, is there any microphone?
Hello. Yeah, so regarding simulation of the open system using QuantumWorks, so how did you put the temperature in the QuantumWorks?
It comes into the coin parameter. So you are doing a coin operator now, which is a unitary coin operator. So where what we do again, then that won't be a completely unitary in the sense because of the dissipative behavior and all. So coin operator will be followed by something like an amplitude damping channel or some kind of noise effect, where your temperature parameters are sitting. So there will be a unitary operator. After the unitary operator, you follow it up with a noisy operator.
I see.
Where your temperature parameter and the coupling, everything.
Yeah. So another point is that in simulating the FMO complex and so on, it is very important to model the bath spectral function very accurately with all the kinks and so on. So how to manage that?
So we have tried to model them in the paper. We have slightly in detail of how we have tried to model mainly the framework for the operational modeling has been there in detail. So, but the way we have tried to look at is not going with the spectral analysis. For us, it's the probability of the transition is what our reference point was. Like how is my evolution operators, which is mapping up with the probabilities of finding it in different sites is obtained. I don't know whether.
No, but what I was saying is that the non-unitary operation is not just a amplitude damping channel or something like that.
It's not an amplitude damping. That's what I'm trying to say. It's not. It's a cross-operated formalism which we are trying to put in there.
And it's usually very hard for this particular problem because you need to keep track of all the weird spectral density of the bath and so on. And so that's actually a bit.
So no, okay. So but what we have for this given system, it's not too complicated in the sense you only have, okay, so there are different approaches which people have tried to see. So there is already experimental evidences which is trying to say that, in the schematic which I had given, there are two particular paths which are prominently taken, the others are not taken. So there is already pre-information which is available. Based on that, you are building a model. Like what you are saying would be that if you don't have any information, then it would be a very universal framework for an open system which one has to build. So in fact, we didn't do that. We are trying to take up the trajectories which is there and mimic the trajectories with it. Of course, again, modeling with just 2 qubits, we are trying to do some approximations there so that you are not, you can't just take 2 qubits and say I'm mimicking a Bathier completely, right? But our intention was try to see in a near-term devices can we implement. So then you have to try to see I need a lesser number of qubit, what is the optimal form. Probably we can discuss more in detail what is there in the manuscript.
Thank you.
Other questions?
Thank you for the nice talk. When you were simulating massive Dirac particle using quantum walk, so was that it was symmetric, right? Like the initial state was symmetric.
Yeah, we took the symmetric state.
You can create an asymmetric as well, and will it still follow?
Yeah.
So will it be an accelerating particle because the group velocity will be increasing?
No, it won't be accelerating. I mean, if you're having in one direction, no.
Yes.
When we're saying a group velocity, you're only taking an group velocity, normalized group velocity, both to the left and right, right?
If the initial state is an asymmetric state, and
It's only a group velocity will be directional in one side, but
yes,
it won't be accelerating. But accelerating is a very different one. In fact, one can actually define an accelerated quantum walk, and that is a completely different one people have done, and we also have tried to study them to try to see if we can mimic Klein-Gordon or some different frame of reference dynamics and view things. But there's no acceleration component here. It's always the group velocity component. The group velocity will be same for symmetric and asymmetric because we are only trying to make there's no direction which comes in the group velocity here.
Thank you.
Any other question?
Yeah.
Maybe I didn't understand. So you said like with 1 photon you can get 3 qubits.
Yeah.
How is that?
So this has been okay. So I would try to. Okay. So the way we are doing here is sorry. Okay. So I am taking a position space, square lattice. So now I have 4 positions. I can just give a basis representation for them. 0, 0, 0, 1, 1, 0, 1, 1. Now this mathematically means nothing for me. I'm just labeling them. This is a classical object for me. Right now, this is my square lattice and this is a classical object.
Yeah, but no, but in the experiment, how do you like?
No, okay. Okay, so this is, okay. Now in the experiment, so now what we are doing for a 3 qubit is I'm taking 4 position space. The square lattice, whatever we saw there, is now split up into 4 paths for a photon. Now, for example, here, there are 2 things here. You can see a single photon is entering, it's splitting into 2 paths, and then I'm taking a measurement. This is just a 2 qubit. Now here, if you see, it's splitting into 4 particular paths. Now, these 4 points you are seeing are the square lattice 4 positions. And other one is a third qubit is a polarization. So now if I have to make a measurement, I need to again have a polarizing beam splitter, measure H and V separately. So I would need 8 detectors to measure a 3 qubit in this alone. So now this 2 becomes 3 and 3.
Related question. I believe you can do universal quantum computation using this method.
Yes.
I see only problem is the number of detectors increase exponentially.
No, I've not even put a picture of the scalability here. So that's exactly what I said. I'm only talking up to the level where 2 plus 2 and 2 into 2 are same. So up to 6 qubit, nothing is making. Now, scalability can be addressed in different ways. One, the moment, as you said, if I am just trying to increase the part degrees of freedom, I need huge number of detectors and I have to deal with it. The other option would be that now I've taken 2 photons and we have created 6 qubit. I can take modules of these 6 qubits with more number of photons. So then I can take 4 photons and have larger number of qubits. But then the gate operations become probabilistic like the standard photonic quantum computing model. So up to 6 qubit level, it's all deterministic for me. I'm not having probabilistic. So that's a big advantage we have to begin with. Now, if I have to start scaling, then I have to play between how much deterministic I'm going to make and how much probabilistic, because I need to bring in more photons to make it more resourceful. And that is a bit challenging task for us now to scale up larger number. We do have schemes for it, 2 different approaches to scale it up.
So the advantage is in between classical and quantum then, because you have probabilistic.
No. When I say probabilistic, it's not about classical and quantum. Existing photonic quantum computing model.
Yeah, but complexity.
KLM model is not a classical one, right? In
Correct.
KLM model, because they deal with 2 photons even for a 2 qubit system.
Okay.
So there the gate operations, 2 qubit gate operations becomes probabilistic. Now here it is deterministic up to some point. Now if I have to make, okay, for example, if I have to implement a gate operation between a qubit here and then in this unit, I need to make 2 photons here and here interact. Then it becomes probabilistic.
Exactly. When it becomes probabilistic, you have to repeat, right?
So you have to repeat so that
it comes below the maximum quantum advantage.
No, but it comes better than any other photonic architecture.
Is there a complexity analysis?
No. What people have done is they have tried to come up with increasing the probabilistic behavior there. But the way I would say is that one, it is better than any other photonic model because photon has this bosonic behavior and that's all. Now there is no noise intervention because in any other superconducting other qubits you are dealing with, there is a lot more noise and architectures are all fixed here. And here everything is in your control. All that I would need is, if I'm converting into waveguides, it's a lot more easier to draw those lines and connect them. So these are advantages. So in spite of being probabilistic, that's what they see photonics advantages here. So as I mentioned, the probabilistic behavior will come in depending on what you have to do, but it will be lower than the standard model which you are.
Okay, so let's thank the speaker again and all the speakers of this session.